Every single day, your heart beats around 100,000 times. By the time you go to sleep tonight, it will have pumped nearly 7,500 liters of blood through your body. If you built a mechanical pump to do that kind of work, you would eventually need to shut it down for maintenance. But this biological engine never stops. It runs continuously, from before you are born until your final breath. To see how it survives this lifelong marathon, we have to look at its blueprint. This animation shows that the organ relies on the precise coordination of three independent systems: a mechanical double pump, an internal electrical grid, and a dedicated logistical supply network. Seeing how these systems overlap explains how the heart meets its mechanical requirements for decades at a time. Welcome to Fresh Vitals. Let's start with the mechanical layout. This cross-section shows the interior chambers, and right down the middle is the interventricular septum. This solid, muscular wall splits the heart into two separate functional halves. The right side acts as a dedicated intake and filtration unit. Oxygen-poor blood returns from the body through massive veins called the superior and inferior vena cava, pooling here in the first waiting room, the right atrium. From there, the blood drops through the tricuspid valve and fills the lower chamber, known as the right ventricle. Then, the right ventricle squeezes. It blasts this used blood up through the pulmonary valve and out to the lungs, where it can offload carbon dioxide and pick up a fresh supply of oxygen. That is the entire job of the right side of your heart. It acts as a specialized local pump to restock the body's primary fuel source. Once the blood is freshly oxygenated, it has to get out to the rest of the body. Here in our diagram, you can see this red, oxygen-rich blood returning from the lungs and collecting in the left atrium. It drops through the mitral valve into the left ventricle. But look closely at the outer wall of this chamber compared to the right side. It is significantly thicker and more muscular. It needs that extra muscle because of the vast distance it has to cover. This left ventricle has to generate enough force to blast the fresh blood out the aortic valve into the aorta and push it all the way down to your toes and up to your brain. Dealing with this massive fluid pressure requires highly specialized hardware. The heart valves act as strict one-way doors. They allow blood to move forward, and then they snap forcefully shut so nothing slips backward. To keep these valves from blowing out backward under the massive pressure of the left ventricle, they are anchored by tiny structures called chordae tendineae, often called the heartstrings. These are pulled tight by papillary muscles on the chamber floor. This spatial layout allows one organ to operate two separate pumps, sending blood to two vastly different destinations without ever mixing the fuel streams. But a mechanical pump with perfect hardware is completely useless if it doesn't know exactly when to fire its cylinders. This diagram shows the electrical grid of the heart. The sequence starts right here at the sinoatrial, or SA node. This tiny structure is your natural pacemaker, generating the electrical spark that begins every single heartbeat. That signal travels down to the AV node, where it intentionally delays the charge for a fraction of a second. This brief pause gives the lower ventricles exactly enough time to fill with blood before they are told to squeeze. After that split-second delay, the signal races down the center septum through the bundle of His and up the outer walls via the Purkinje fibers. This wiring forces the muscle to contract from the bottom up, pushing the fluid effectively toward the exit valves at the top. This autonomous electrical grid dictates the rhythm that maintains fluid dynamics and prevents the muscle fibers from contracting out of sync. There is a biological irony to this structure. Even though the heart is constantly filled with gallons of fresh blood, the thick muscle tissue of the chamber walls cannot absorb oxygen directly from the fluid rushing inside it. To survive, the heart relies on a third mechanism. This rendering shows the logistical system, a dedicated external plumbing network of coronary arteries. They branch out from the aorta and wrap entirely around the outside of the heart, feeding the muscle tissue itself. One of the most critical supply lines in this network is the left anterior descending artery, or LAD, which runs straight down the front wall. Medical professionals often refer to the LAD as the widowmaker. If a blockage occurs here, it instantly starves the massive left ventricle of oxygen, bringing the entire body pump to a halt. The heart is an engine that must continuously fuel itself while it fuels the rest of the body. If its internal supply lines fail, the whole system collapses. This schematic shows the complete circuit in action. Used blood flows from the body to the right heart, out to the lungs for oxygen, back into the left heart, and finally gets blasted back out to the body. Absolutely every single cell in your body, from your optic nerve to your fingertips, relies entirely on this sequence continuing without interruption. Over the course of an average human lifespan, this sequence of mechanical pumping, electrical timing, and logistical supply will repeat roughly 3 billion times. This specialized architecture is why the heart remains the most durable pump in the natural world. The best way to protect your anatomy is to understand it. If you want to keep exploring the machinery inside you, like this video, share it with a friend, and subscribe to Fresh Vitals for more organ-by-organ lessons. Thanks for watching.